So I wanted to talk to you about using GNU Radio for radar applications. Now, one reason why I wanted to share with you this insight during this conference is that last March, I believe, we were at CERN at a White Rabbit workshop. I'll talk about White Rabbit. And usually when I do my passive radar measurement, I have X310s, so Etudes Research X310 software-defined radio platforms, dual channel, and I'm using the White Rabbit network for synchronizing. So White Rabbit is a system developed by high energy particle physics laboratories, including CERN, including GSI, for synchronizing these software-defined radios. And as most often during these conferences, the guys at GSI, including Dietrich Beck, were presenting the development in GSI about White Rabbit. And when I realized that the conference, GNU Radio conference, would be held in GSI, I had to put these two together. So the team of White Rabbit developers of GSI were kind enough to send me a few of their boards. These are all GSI boards. And what I'm going to show you is how we can synchronize software-defined radio receivers for coherent measurements using the White Rabbit boards, PCI Express boards dedicated as developed by GSI. And of course, here I want to highlight the unique opportunity at GSI of having the developers of GNU Radio 4, of having the developers of White Rabbit in the same location. So I hope you can find some way of merging these two activities. So radar, usually radio frequency detection and ranging, is considered as a way of measuring the distance to a target. And it's common to say the range resolution is the speed of light divided by the bandwidth of the signal, divided by 2 because it's a two-way trip. And the problem with this broadband radar, where you want to maximize the bandwidth in order to have as high a range resolution as possible, is that if you increase the bandwidth, you also increase the noise that you integrate in your measurement. And if you integrate more noise, well, your signal-to-noise ratio is degraded. So an alternative to this is to consider narrowband radar. So if you have a narrowband radar, the problem is the bandwidth goes to 0, and that means that you might not have any range resolution. One application of this narrowband radar is interferometric measurement. You want to do just a phase measurement, so you don't care about the absolute position, but you just want to detect the displacement at the expense of half-wavelength uncertainty, because you have two-way time of flight. Another application is that the laboratory I come from, which is time and frequency, so our activity is to have high ultra-stable clocks, ultra-stable oscillators, so the ability to timestamp events with high accuracy meaning sub 100 picosecond, and high stability clocks. And one activity here is to use these high stability clocks for detecting fine frequency shifts. And what are the frequency shifts that we're interested in is moving target. If a target is moving, then you have Doppler shift. And if you can have a fine Doppler shift measurement, you have a high velocity measurement, high accuracy velocity. Now, from the laboratory I'm located in, 40 kilometers away, there is the Space Surveillance Radar Emitter in France. We have the GRAV, Grand Radar Adapté à la Veille Spatiale, which is a military radar, to the best of my knowledge, is 400 kilowatt transmitted at 143 megahertz from 40 kilometers from the lab. And it's a bistatic radar with a receiver south of France in the former missile silos, Plateau d'Albion. And this bistatic radar requires high stability in order to compare the Doppler shift introduced by any flying object, any object flying over the metropolitan French territory, including spy satellites. So, of course, this system is used to detect whatever is flying over the territory. So what I'm interested in is, I'm located over here, the GRAV radar is over here, and illuminating anything that is flying over our territory, including planes. And if we don't have any range resolution for a satellite, all you want is to detect Kepler parameters. So from a few velocity measurements, you get all the parameters of a satellite orbit because they follow the third Kepler law. In our case, we would like to have locations of planes, and if you want to have location of planes without range information, you need to do direction of arrival or time of flight measurement. So multistatic radar is a very well-known topic. This is a NATO textbook about multistatic radar. So it's a field that is pretty well-known, but just so that you can follow the discussion, I have to remind you, if I have a multitude of antenna to get azimuth information or azimuth and elevation information, then if you assume that a plane wave is reaching this array of antennas, then you introduce a phase shift which is related to the angle of arrival and the distance between the antennas with respect to the wavelength. And in the classical case of a uniform linear array, ULA, then this phase shift is a constant between each antenna. Now, if you have something with a phase at the nth antenna, which is n times delta phi, well, if you think of what is a sine wave is a constant increment of a phase as you have constant sampling in time domain. So what you have here is exactly the same thing as a sine wave. If you want to know what is the frequency of a sine wave, you take the inverse Fourier transform. Exactly the same story here. If you take your measurement of a phase along the various antennas and you want to know the direction of arrival, it's an inverse Fourier transform in the space domain, not in the time domain. So what is the actual measurement? A multistatic radar measurement is collecting a matrix where you have n antennas, each collecting p samples, time domain. And if you want to do migration from antenna position and time towards direction of arrival and frequency, then you take a 2D Fourier transform. So this is why whenever you look at SAR or synthetic aperture radar or multistatic radar, you will see inverse Fourier transforms. And this assumes that over the integration time, your environment is static. So if you take Fourier transform, you assume that your direction of arrival is a constant. So if you have a periodic sampling of a sine wave and you take the inverse Fourier transform, and since Gauss, we know that there is an efficient way of using the symmetries of trigonometric functions, which is called the fast Fourier transform. If you take the IFFT of a sine wave sampled periodically, you get a Dirac function. And this is known to be an n log n complexity algorithm. However, the assumption here is that you've collected each and every sample periodically. If you think of this in terms of antennas, it means I need to have as many antennas as the red dots in the space domain. I need to buy a lot of X310s. And the last time I checked, X310s are 10K euro. That's going to be a very expensive radar. Now, another expression of this is you can express a Fourier transform not using the symmetries of the FFT, but going back to basics. You're multiplying your samples with a matrix where you have the time over this direction, incrementing at a fixed frequency, Fourier frequency. And on the x-axis, along the columns here, you have frequency 1, frequency 2, frequency 3. And you can express a Fourier transform as a matrix multiplication. Now, if you keep the bijective properties of a matrix, it's a square matrix. You have as many times as you have frequencies, and it gives you exactly the same frequency. I offset so that you can see the difference between the two curves, but whether you're taking IFFT from MATLAB or you're taking the matrix multiplication, you get the exact same result. Why is this a useful information? Because no one said you needed to match the properties of a Fourier transform, that there's as many frequencies and times, and no one said that the time has to be regular or that the frequencies have to be evenly spaced. You can say, I'm going to have randomly timestamp data. What's important is you need the timestamp. You cannot say, I randomly sample data. If you know at which time you sample the data, no one said you needed to have all the red dots. Okay? So let's say that, for example, I only collected a few of these samples. So I keep all the output frequencies as before, but now I have fewer points, fewer samples. Of course, you all know that if you gate, the Fourier transform of a gate is a sinc function. So by having fewer samples, you have, well, the spreading with the side lobes due to the sinc function. But now we have a rectangular matrix. We have many more times than we have many more frequencies than we have times. We can do this a bit further by saying, well, maybe I only have a couple of samples over here and a couple of samples over here. What's very important here is don't tell anyone that I'm not meeting Shannon's criterion. Of course, these two samples are nearby, and this is why I still have high equivalent sampling frequency. However, I'm creating artifacts because these samples here are now separated by widely unknown quantities. So you spread the sinc function, but still you can operate this calculation. And now you see I can have information about the inverse Fourier transform with only 4 samples. 4 samples in the time domain. Remember, this is 4 antennas in the space domain. So now we have an expression in the matrix domain where I have all the frequencies and the dual quantity in our analysis is the direction of arrival for very few antennas with the disadvantage of the side lobes. And now if you say these two antennas are further apart, which is what you do with VLBI, you say I have two antennas which are not nearby but now further apart. Well, you've got these comb of functions here, which are now you've got the high resolution of the far away VLBI antennas, but because they are far away with missing dots, well, you've got the envelope. And this envelope, what is the envelope? Of course, if I just were to take one antenna here and one antenna here, you've got aliasing, you lost the high sampling frequency of the two nearby antennas. So now that I went quickly through the mathematical basics, why is this useful? Well, what your colleagues at GSI here, Dietrich Beck and his group, lent me is this White Rabbit board. Why do I need this? Because I'm going to have widely spaced apart antennas, and I want them to be phase synchronized if I want to have direction of arrival. Now, typically, it's considered that White Rabbit will give you something out of the shelf of in the 50, 60 picosecond time resolution. So it means White Rabbit will send a signal out of a source. It happens that the lab I come from is dedicated to high stability frequency, so we have access to free hydrogen maser, we have access to cesium clocks compared to the Paris primary reference. So this is my master clock. My master clock goes to a White Rabbit switch. My master clock is located over here. So the 1X310 receiver, which is an antenna located over here, is 50 meters away. Now remember, light is propagating 300 meters per microsecond in air, 200 meters per microsecond in a optical fiber. So 200 meters per microsecond, if I go 50 meters here, I already wasted 250 nanoseconds. And I said White Rabbit gives you 60 picosecond resolution. Well, what happens is that White Rabbit is measuring the time of flight and compensating for the time of flight. So this is my first antenna array, 1X310, two antennas located over here. And then we have the Besançon Observatory located over here, 600 meters away. 600 meters is 3 microseconds in an optical fiber. But again, White Rabbit is compensating for the time of flight. And we have our high accuracy timing capability at the Besançon Observatory. And this is my teaching class at university, where I have also access to the roof, so I can put another set of antennas 600 meters away. So you see that we can create, using White Rabbit, an array of antennas, two antennas over here, two antennas over here, each fitted with one X310 dual channel input, and we can try to do some measurement. These are the outputs of the GSI PCI board, which are running White Rabbit core, and you see that, well, they're locked, good. And you see here that the phase tracking is enabled, meaning that the White Rabbit are indeed getting the right signal. And here you see we have something, if you remove this is picosecond, so this is 820 nanosecond. 820 nanosecond is the time of flight from this location of a miser here to here. And here you have 650 picoseconds, and here you have 10 microseconds. 10 microseconds is, if you remember, 200 meters per microsecond. That's about 5 kilometers. If you don't have straight line over here, well, that's the path followed by the optical fiber two-way trip. So you see here I did the calculation for you. So you see here we have our two White Rabbit boards, which are clocking the X310s, and indeed we do have phase synchronization on all the X310s. So what can we do with this? Now, just be a bit careful, and this is not a negative comment with respect to the GSI work. I should emphasize the GSI boards are amazing for what they're doing. I just want to warn you that I really want to have something that is hardware agnostic or vendor agnostic, and even though CERN and GSI are using the same White Rabbit core firmware, well, when the first time I ran this, these are the 1 pulse per second from the CERN White Rabbit switches. These are 1 pulse per second from the GSI board. They're aligned to better than 1 nanosecond, so they're doing the job the way they want. However, you see that this is one hardware, this is another hardware, and there is a time offset between the two. So I just warn you, be careful that when you're using the same gateware on an FPGA running on different hardware, well, you introduce, we're talking here about nanoseconds, and one nanosecond is 20 centimeters on a PCB. So be careful that there are some latencies that are introduced, unwanted latencies, and the GSI people told me, yeah, we know we have to repair this, but just be aware that you have to be a bit careful about the impact of running the same firmware on different hardware. So having said this, in which context can I use this? So Grav radar is broadcasting at 143 megahertz. You might know if you're a ham radio that sometimes people compare their clocks or their oscillators to the Grav reference signal. Now, Grav is broadcasting a signal at 143 megahertz, and the X310 is sampling at 200 megasample per second, which is Nyquist frequency of 100 megahertz. So if I want to record the 143 megahertz, I'm actually going to use on purpose the second Nyquist zone. So it's aliased signal. And the Doppler shift, when you're doing radar measurement, you have to remember that the signal is going two-way. It's going towards the target and coming back from the target. So the frequency offset is actually 2 times the carrier frequency times the velocity divided by the speed of light. And it happens that because the velocity is about 150 megahertz, the frequency is 150 megahertz, 2 times 150 is 300, divided by 300, it happens that the frequency offset of Grav is about the velocity of a target in meter per second. So if you think of subsonic aircraft, so sub 330 meter per second flying aircraft, well, you expect a Doppler shift about in the 300 hertz range. So you're sampling your megahertz signal, and then you need to decimate until you reach a few kilosamples per second. And one nice thing with White Rabbit, it's a gigabit Ethernet switch, meaning that you can also broadcast the data over the fibers of White Rabbit. I don't need to go through all the firewalls that you've seen. I have to go through the Besançon Observatory. I have to go to university. The nice thing with the White Rabbit switch is a gigabit Ethernet. I have a few kilosamples per second. I just run my stream of data over the White Rabbit network. If you do a quick calculation, 60 picosecond standard deviation of phase synchronization at 143 megahertz gives you something like 3 degrees of phase stability between the various receivers. So this is what the GNU Radio flowchart looks like. Be careful that if you want to synchronize multiple USRPs, you need to run a multi-USRP source, because the computer running the multi-USRP source is going to broadcast the signal to all the USRPs to synchronize them. You see that the center frequency is 56.95 because I'm using the second Nyquist zone. And as we all know, because if you want to decimate by as much as, you see here 25 divided, so that's 125, 1,000. So if you want to decimate by 1,000, either you put one filter with a huge number of taps, or you cascade and decimate. And this is what I'm doing here. I'm cascading and decimating my low-pass filters until from the few 100 kilosamples per second I collect initially, I end up having something like 640 hertz baseband. So now that we have all this data, here is a typical measurement. These are 3 of the 4 antennas I put on the roof. And because you're only 40 kilometers from a 400 kilowatt radar, you just put a monopole on the roof, and that's enough to get the signal. Now, you will have here all the tracks. These are waterfall plots, sorry. So this is the frequency, this is the time. And as I told you, the frequency happens in the Grav radar to be equal to the velocity in meter per second. And you have here the time, you have frequency, and these arctangent functions are actually the projection of the straight flying plane on the baseline between the emitter and receiver. When you've got this kind of kinks over here, this means that actually the plane has turned and the projection has changed. And when you've got this big blob here, this is a fighter jet, because fighter jets, they don't fly straight, they just keep on moving in all directions. And so your Fourier transform doesn't integrate in one nice peak in the frequency domain, but you've got a whole range of velocities. And this actually is a direct wave, direct from Grav emitter to our receiver. And this is a beautiful straight line because we're locked on the hydrogen maser. If you were to run this on a standard TCXO, on a temperature controlled crystal oscillator, you would see this line drifting in all direction because you have intrinsic local oscillator motion. And so this beautiful straight line, which allow fine Doppler shift measurement, are thanks to the high stability local clock. So if you want to know why we're being paid for making high stability local clocks, high accuracy Doppler shift is one reason. If you don't have a fighter jet, this is the kind of peaks that you get. Each one of these is a plane flying towards our receiver. So if you do this over time, you've got time domain over here, you've got the three of 4 antennas, and each one of these is a plane coming towards us, crossing the baseline, so 0 Doppler shift, and then going away from us. This is super simple octave script for just taking short-term Fourier transform. But what's amazing, this is just incoherent, this is just magnitude as we've seen with the optical fiber presentation yesterday. But because now we're coherent, we can actually do phase measurement. And if you take the phase difference with respect to the first antenna, this is 2 minus 1, 3 minus 1, 4 minus 1, you've got these beautiful curves that start here at minus 3 radian, that move slowly towards plus 3 radian, and then you've got phase wrapping. So you see that we can expect to have a beautiful direction of arrival measurement, and this is just angle of the IQ stream, second antenna divided by first antenna, so phase subtraction. So now that we have these beautiful, continuously varying phases, what can we do with it? The first thing is we might want to have azimuth elevation. So in this example, I didn't put my 4 antennas far away. I put them just co-located on the roof of our university. So you have here a square 1, 2, 3, and 4 antennas separated by 46 centimeters, that's quarter wavelength. And if you think of it, you have a plane coming towards your square baseline. You just do some quick projection. You've got theta the elevation, phi the azimuth, and you say that you've got the x, y, z baseline, z equals 0 because they're all on the same plane. So you can very easily calculate that from your phase measurement between the 4 antennas, you end up having azimuth and elevation. So we've got here azimuth and elevation, we've got azimuth as estimated by 2 of these antennas, we've got elevation as measured by 2 of these antennas, and then you can end up plotting for the whole time what is the evolution, so the velocity as a Fourier frequency, azimuth and elevation. Now this is such a crowded chart because there are so many planes flying over our university, there's nothing you can see with it. Except during the night. During the night, there's few enough planes that you can separate the individual contribution. And if we zoom in, well, that's the kind of velocity fluctuation, that's our azimuth information, and that's our elevation. That basically gives you an insight about the path, the track that is being followed by the plane. So that's a 2D information, but it's not benefiting from the fact that we have multi-antenna. Now we're using the square baseline pattern, and this gives us a 2D position of a plane. Now, if we go back to the initial insight of saying we have a uniform linear array, possibly with a gap, when we do the same story as we did before, we take the inverse Fourier transform. And again, this is another 24-hour measurement with the antennas this time aligned on the roof. And you can do the same story, except that now you only have azimuth. You don't have elevation anymore because all the antennas are aligned. And again, we have overnight the gap. And we can look at what is the evolution of the angle of arrival and the frequency offset. So you've got continuous lines that hint at a properly measured angle of arrival from array using direction of arrival. And as I told you, if you spread further the antennas, if you spread them further away, so now I put 2 antennas 50 centimeters from each other and now separated by 7.5 meters, as you can see here, we've got the frequency shifts of the velocity, and you have here the result. And you remember, as I told you earlier, if you've got these 2 samples far away, you've got a comb of sharp peaks, and this is actually your comb. So here you have one of the direction of arrival estimates, except that this is over an envelope, and this envelope you have to do some feature tracking to only follow one track and not the other one. So that's exactly why we have these lines parallel, because one of them is the path of a plane, but we have uncertainty because of 2 far away antennas. Finally, I told you that quite a few people, ham radio, are using grav radar as a frequency reference, and I was wondering whether I could use grav radar for frequency dissemination. Now, what makes this slightly difficult, if you look on the internet, you'll find some document that says that grav radar is actually sweeping a beam, and because you're sweeping the beam, it's an electronic phase array. The problem with electronic phase array is each beam is phase coherent, but from one beam to another, you don't really know what's happening. The electronics is introducing phase. So if you zoom into a time domain evolution of a phase of the signal that we received, this time we're not looking at the planes, but we're looking at the direct wave from graph to receiver. You see that actually you see the sweeping of a beam. This is beam number 1, number 2, number 3, number 4, number 5, number 6, and then it repeats again. So actually you have 8 beams, and you need to select out of the phase one beam, and then you measure the phase stability or the oscillator stability of the oscillator clocking graph, and you try to detect what is the stability. If you do this analysis, I'm not going to get into the details, what makes it a bit tricky is that you get a wrapped phase. Even though we have a hydrogen maser, well, your phases are always drifting one respect to the other. And this is the unwrapped phase. And if you look at the Allen deviation, so Allen deviation is how much does the phase fluctuate as a function of integration duration. So on the x-axis, you've got the duration of a sliding average. On the y-axis, you've got the relative stability. And you see that graph radar time transfer gives you something at about a few 10 to the minus 11 at 10 seconds, decaying as a square root of tau integration duration. And my colleague Claudio Calosso from the National Italian Institute tells me that one of the square root of tau is typical of a link-limited stability, meaning that we're not measuring actually the graph stability, but we're measuring all the noise and all the uncertainties of a broadcast signal between the emitter and our receiver in Besançon receiver laboratory. Just to give you an insight, this is the Allen deviation of a hydrogen maser at 10 to the minus 13. So what we're measuring is not our local hydrogen maser, but it's definitely the graph link. Our hydrogen maser is more in 3 orders of magnitude, more stable than what we're measuring here. So as a conclusion to this presentation, I wanted to show you how GSI has this unique opportunity of having in the same location White Rabbit and GNU Radio. I'm giving you this example because I don't have an accelerator at home on radar measurements, but I think that merging time synchronization using White Rabbit and software-defined radio opens a whole field of opportunities. Now you could, White Rabbit has been now standardized as PTP high availability, but it's becoming more and more widespread thanks to this. I wanted to try to show you how this measurement can be applied to 1D or 2D analysis, and actually how you can do time transfer using this system. Now, White Rabbit at the moment is only used as one part White Rabbit generating 1 PPS and 10 megahertz. On the other hand, the X310 receiving 1 PPS and 10 megahertz, which is fine for an X310, which is actually used for receiving anything. But what if you want to have something other than 10 megahertz? And part of my work is to try to see how I can generate any random frequency. There is one chip from Analog Device, which is called a network clock synchronization chip, that will generate anything between 0 and 400 megahertz locked on the 1 PPS and 10 megahertz. And one beautiful development at CERN, at least I'm aware of what they're doing at CERN, is called this RF over White Rabbit, where instead of having peripherals clocked by the White Rabbit signals, they actually integrate they integrate the radio frequency, DDS, or numerically controlled oscillator inside the same FPGA receiving the White Rabbit clock, meaning that actually you put in the same FPGA all the capability of time synchronization and radio frequency acquisition or generation. And my vision here would be to have the White Rabbit core as one of the plugins, or ideally for RF NOC, but that's maybe too much to ask, on a general purpose FPGA. Here, these FPGA, the only drawback is that they need 2 external programmable oscillators, and the vision is modern FPGA have fine enough PLL that you can get rid of these external oscillators, and that means that any FPGA fitted SDR should be able to run White Rabbit synchronization. So that would be the perspective of this work, and for FPGA specialists, fine development if you're interested. And with this, I thank you for your attention.